And you don't have to turn in this worksheet because I think this worksheet should be very helpful for you to review for the final. I looked it over, and it basically has a sample problems from every section in the chapter. So by going through reviewing each of the chapters, there's like 2 or 3 problems from each section. If you want, we can even do some more matrix problems, but I figured we'd go back and do just the section before and just little by little go back into the past of what we've been working on. So some log problems, some function problems. Remember those combinations and compositions of functions? We'll do a couple of practice of those, and then a little bit of polynomials, and there is at least one problem having to do with that investment formula. So we'll get to that as well. Give you practice on each of these. This is being recorded, so you can always go back and say, okay, let's go over that one again and practice how did you get that answer. So I'm planning on going in this order, and I'm planning to stop and give you a chance if any of these are at all confusing or if there's something I haven't covered that, hey, there was a particular problem, I can always go back and work on one. So this is a note for you to keep, and you can always use the recording as well. So what I would do here, looking at the problems, and again, it's going to be open note. So if you have these if you want to put these formulas on a note or even have this worksheet for you as here's how example problems go, will be welcome to do that. But as you review, let's look over our laws of algorithms. Remember the whole deal with logarithms, the whole deal with logarithms as we have some kind of exponential equation, like a to some power x equals y. Logarithms help us solve problems like that. When we say logarithm base b of some number that I like to put in parentheses x, they don't always put that in parentheses, of x equals y. Remember what that means. That is the same as, and I can go either direction, that's the same as b, the base, that's our base to some power y is equal to that x. And you can draw the little lines, b to the y is equal to that x that's in there. And what I love to remind myself, just remembering that log of 100 equals 2. Count the zeros when we're dealing with logs. And remember, if we don't see a number there, we know that that is automatically, I'll put in dotted, it's automatically a 10. If you don't see a number there, it's base 10. Log of 100 is 2. Oh yeah, 2 zeros, 100 is 10 squared. 10 squared equals 100. There's other formulas, though, that we'll also be wanting to use. And we can write these down or have them in our notes. The very basic rule is the log of a times b, the rule of logarithms, that's the same as the log of a plus the log of b. Two numbers multiplied together, I can make it into an addition problem using the log formula. But remember, it also goes the other way. If I'm adding two logarithms, that's the same as the log of those things two multiplied together. So solving some problems, sometimes we need to go this direction. And you could throw in there the log of a divided by b is the log of a minus the log of b. And again, I can go in either direction. If I see a subtraction of a logarithm given to me, I can think to myself, oh, they might want me to go this direction, knowing that that's the same as a divided by b. And when I have something like log, I'll call it log of, I guess we can go, yeah, we'll go x. Log of x, if I know log of x equals log of y, the only way for that to be true is that x must be equal to y. So if I ever see a problem where I have some log x equals some log y, I can decide, wait a minute, I don't have to worry about logarithms anymore. If I'm trying to solve some equality, I know that what's inside those means they're also equal. We'll be using those in these practice problems then. So you could have these in your notes to help you review them. I always find if I write it out, I remember it a lot better. If I just type it in or just read it, copy paste it, it doesn't stick. But if I write it down, my mind clicks a little better on it. So let's go through some practice problems. After writing those down or having them on a note, you can bring these on your notes ready to go. You don't have to write them out. Now let's do a few problems. Log base 2 of 5x equals 2. We need to solve for x. When you see something like this, what do you think? Well, I don't have log on both sides, so I can't use the equality of logs. I can use the basic definition of logarithm here. When I see this, I know that 2 squared equals 5x. So I can say 2 squared equals 5x. Well, 2 squared isn't that hard. 2 squared is 2 times 2 equals 4 equals 5x. Now divide both sides by 5, and I have 4 divided by 5 equals x. And I am done. So in this case, we actually do the squaring because there's nothing else possible to, because that's our rule, log base b of x equals y, b to the y equals x. That's our rule that we remember that we have up there in our notes. So b to the y equals x. And in this case, what's inside of that is that quantity. 2 squared equals what's inside of the parenthesis. And then it becomes just a solve for x problem. Now they're usually going to be nice to you and not give you huge numbers. They'll either likely do a cube or a square. But if it goes higher, don't be embarrassed. Use your calculator. You don't have to memorize all the cubes and to the 4th powers. But squaring of a small number wouldn't be hard to review that. But again, you can even use your calculator for that if you need to. The problem with me is if I don't do it in my head, I have just as much chance of messing up on my calculator, hitting the wrong key, as doing it in my head when I have smaller numbers. So there's our answer right there. All these on this row are the same type of problem. I see a problem like this, log base. I right away think 3 cubed equals 4x. Base to that number is equal what's inside of the parentheses. 3 cubed equals 4x. 3 times 3 times 3. 3 times 3 is 9, times another 3 is 27. So 27 equals 4x. And just divide both sides by 4 to get x by itself. 27 fourths equals x. And I can't simplify that. If they asked it for decimals, I could put that in my calculator. But this is as reduced a fraction as I can get because 27 is odd, and 4 does not go into 27 an even number of times. Hoping that's coming pretty easy for you. The key is, when you're going to get this problem, just to remember, you see that form, when you see the basic form of logarithms, the only thing you can do is apply the basic definition of a logarithm. In this case, 4 squared equals 3x. Now that might get fancier inside of there. That could be 3x minus 1. Anything inside the parentheses is going to be what's on the right side of the equality sign. Square 4, I get 16 equals 3x. And divide both sides by 3, I get 16 thirds equals x. 16's even, not divisible by 3, so that's as reduced a fraction as I can get. And one more of this form. You know what? I think I'll come back to that. We'll do another one. Then we'll come back to this form just to refresh. Because again, doing a problem and then going on and then coming back to it is even better for your memory, for your practice. Doing all the same, it just becomes, oh, that's easy enough and don't think so much. We'll come back to that last column. Now the next one, you're going to give the problem just a slightly different format. And what comes to mind here? Looks a little scary, but don't be scared. What do we see here? When you're adding logarithms, think to yourself, oh, that's the logarithm of those things, two things multiplied together. The log of AB, I'll just write that down just for my notes. Log of AB is the same as log of A plus log of B. Oh, and I have two logarithms added together. Well, let's try that. Log, now remember the base, don't forget to keep that base in mind. Those two things multiplied together is x times x minus 6 equals 4. Hey, now I'm back to a problem that looks a lot like this. I have the base, and I have the base to some power equals what's inside of that parentheses. So let's write that out. And I'm going to need a few more lines, so I'm going to write it just a little bit smaller. This is 2 to the 4th equals what's inside of that multiplied out. So I'm going to go ahead and do the multiplying while I set the equal. That's x squared minus 6x. Well, 2 to the 4th is the same as 16. 2 times 2 is 4, times 2 is 8, times 2 again is 16, equals x squared minus 6x. Well, now it becomes, if I subtract 16 from both sides, I have the formula x squared minus 6x minus 16 equals 0. Now at this point, I could crank it through my quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Or I could attempt to do some factoring. Well, let's see here. I'm looking for two numbers that when added together give me a negative 6. When multiplied give me a negative 16. And I see that 16 is 2 times 8. And the difference between 8 and 2 is a 6. So if I subtract an 8 and have a positive 2, negative 8 times 2 is giving me negative 16. Negative 8 plus 2 gives me negative 6. So I can see by factoring that that's x minus 8 times x plus 2. And therefore I know two possible values for x are 8 or negative 2. But remember what I have to do still with logarithms? I have to say, does a negative 2 work for a logarithm? Uh-oh. 2 to some power is never going to give me a negative number, so I have to throw out the negative 2. So now I know the solution for x is 8. Remember, we can't do logarithms of negative numbers. And that's the basic step when you see this. It's the rule of the product. we build it up carefully, come up with a polynomial equation, solve for x, and throw out any negative values of x. Now, if both of them worked, then you would say, hey, it has two solutions. That would be perfectly fine. But usually we throw out one. I'll give that another one a try. You good with that one? Notice you recognize the product rule. So let's just go ahead and do that. Log base 3. And we have these two things multiplied together. Be very careful to make sure to put parentheses around the x minus 6. Otherwise, things will just go wrong, and n equals 3. And now we apply the definition of logarithms. 3 cubed equals, and let's go ahead and multiply it out, x squared minus 6x. Or 27, 3 times 3 is 9, times another 3 is 27. 27 equals x squared minus 6x. And now, to turn it into a form like this, I got a little room here, x squared minus 6x minus 27 equals 0. And now, can I factor it by hand? Or do I use the quadratic formula? Well, let's see here. Two numbers added together give us negative 6. Multiplied together give us negative 27. Well, let's see. The factors of 27 are 1 times 27. It's not a multiple of 2 because it's not even. 3 times 9. Hey! 3 subtracted, or negative 9 plus 3 gives me negative 6. So, negative 9 and a 3 added give me negative 6. Multiply give me negative 27. So, therefore, I can factor that x minus 9 and x plus 3 times x plus 3. Again, you could have cranked this right into the quadratic formula. And let's just show the quadratic formula down here. Negative b, that would be 6. This is the b value. Remember, that's a, b, c. Negative b, that's 6, plus or minus the square root of b squared, that's 36, minus 4 times a negative 27, that becomes a plus 4 times 27, all over 2a, which is a is 1, all over 2. Well, since I know the factoring, I know that that's going to come out to be a 9 or negative 3. 3 plus 4 times 27 is 80 plus 28, 108 plus 136 plus 36 is 142. Or is that 144? Yeah, 144, which is square root of that is 12. 6 plus or minus 12 all over 2. And I know that's going to come out to be 9 and negative 3. So, x equals either 9 or negative 3. And we know, negative 3. And we know, there we go, we can't do a negative 3 inside of there. So, only possible value for x is 9. But I could have cranked it through the quadratic formula, and I would have gotten 6 plus or minus square root of 144 over 2, which ends up being 6 plus or minus 12 over 2. And I'll just put it that way. It's 6 plus or minus 12 all divided by 2. 6 plus 12 is going to be 18 divided by 2 gives me 9. 6 minus 12 gives me negative 6 divided by 2 gives me negative 3. But throw out the negative 3. These, so far, are the most complicated ones, but it gets us back to a quadratic formula problem. And when we get to here, don't worry if you don't recognize the factoring. You got your quadratic formula to work with. And you know what? Since we're going to use a quadratic formula, that's something that I would put in my notes at the top I got a little more room over here. I'd write in my quadratic formula. When I have a problem, a times x squared plus b times x plus c equals 0, the quadratic formula for the solutions is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. That would be a good formula to have in your notes when you come across any kind of problem like this. Remember what we're seeing here, and we'll be seeing this later. A formula like this is some sort of parabola, either going up or down, and what we're finding is where it crosses the x and y axis, those are when it's equal to 0. So we're finding those 2 points. We'll come back to this little graph later in another problem. There is a problem that says, given a formula like this, where's the vertex? Well, we know that the zeros, halfway between these 2 zeros is my vertex, and I know the value of that vertex is negative b over 2a. Because this is negative b over 2a plus or minus the square root of all this, and this is negative b over 2a minus the square root of all this. So we know negative b over 2a is exactly in the middle, and that's going to be our vertex. So this isn't a bad thing to remember, that is our vertex. That's the formula for the vertex. Okay, let's go back to one more of this practice problem, and then they do get easier. I'll zoom in a little bit so I can write a little finer. Okay, so this one here, again, I recognize logging or adding 2 logs, the same base. They usually aren't throwing a trick problem at you with the 2 bases different. If the 2 bases are different, there's not much I can do. But the base is the same. Now I know that that's the same as the log of x times x minus 6, base 2 equals 4. Hey, it looks a lot like this, but it's a different base. I better get a different answer. So now I know 2 to the 4th equals that. 2 to the 4th equals, inside of there, multiplied together, x squared minus 6x. And this turns out to be 16. Hey, is that the same as the one over here? Oh, I should have made that different. Sorry, well, I'll just say C column 1. So we can stop here and realize, hey, wait a minute, that's that same problem. So I'll just put in here, C column 1. This is the same problem. Same problem. But we approach it the same way. Oh, yeah. That's how we solve that. So there we realize, oh, we got the same problem. All right, so we'll come back to that one as we do it. If we have more time to review, because the more you review, the better you'll do. Okay, now this one, well, I don't have a number on one side. I have logs on both sides. Well, when you see something like this, think to yourself, if I can get it into some format like log of something equals log of something else, then I know that those 2 somethings are equal. I can throw out the logs and know that, hey, what's inside the parentheses are equal, and I've simplified my problem. So we see that. We have logs on both sides. When you see logs on both sides, let's use our rule of multiplication, and we have log of x plus 6 is equal to log. Addition of logs means the same as the log of those things multiplied together. That's the same as log of 7x. And now, look at that. It becomes actually an easier problem. I know what's inside of this is the same as what's inside of this, so I can just say x plus 6 equals 7x. Logarithms are gone, and I have a simple problem. Subtract 1x from both sides, and I get 6 equals 6x. You subtract x from both sides, so I have 6 left over by itself. X's go away. This becomes a 6x. Now we divide both sides by 6, and I get 1 equals x. So although this looks scarier, this is actually a simpler problem. If you remember, oh yeah, logarithms added together means it's the logarithm, those things multiply. And then I can set the insides of the logarithms equal. And remember, the rule is the bases have to be the same. And I think all these problems, we have the bases be the same. Notice another thing here, it doesn't matter what base was being used. If I can get to this form, and as long as the number of the base is the same, I can throw away logarithms. Let's do the same one on this one then. Oh yeah, log of x plus 3 equals the log product rule. That's the same of log 5x. I could have written log x5, but that's often confusing. We like to put our numbers first in our letters. So I'm going to write that as log 5x. Remember, the order doesn't matter. But now that I have two logarithms equal to each other, now I can say x plus 3 equals 5x. Subtract x from both sides to have a 3 by itself here. So subtract x, and I get 3 equals 4x. And divide both sides by 4, and I get 3/4 equals x. And you'll be given a couple problems of each type on the final. And now doing it the third time, it's like, let's make sure we're not doing the same problem as before. No. But again, I can see, oh yeah, log x minus 3 equals log 4x. Set them to be equal now, and I have x minus 3 equals 4x. And, ooh, negative 3 equals 3x. And therefore divide by 3, I get negative 1 equals x. So don't let the subtraction mess you up. Keep that in there so you don't lose your sign. We subtract x, leaving us still the negative 3. 4x becomes 3x. Any questions so far? I'm hoping just by practicing, you'll build your confidence, and then and remember the strategy for your tests. Do the easy stuff first, come back to the hard one. Don't get stuck and frustrated and anxious on a hard one. Figure, okay, I'll come back, and as I'm working the simple ones, the hard ones will become easier. What do I do here? If they say I want the calculator, I could just do log base 2 of that plus log base 2 of that. Or if they want the exact solution, well, what can we do? Well, use the product rule. That's the same as log base 2 of 7 times 12. And 12 times 7 is 2 times 7, 14, 1 times 7 is 7, 8, 84. So log base 2 of 84. Is there anything I can do with that? Well, let's see here. Can I find the factors of this? 84, well, we know 84 is 12 times 7. That's also the same as 3 times 4 times 7. Well, there's a 4 in there. And 4 I know is 2 squared. Oh, I could do logarithm of log base 2 of 3 plus log base 2 of 2. Oh, log base 2 of 2 is 2, and log base 2 of 7 is calculator thing. I could say, if I wanted exactly the most simplified answer, it would be, well, let's write this out so it's clear what we're doing. I figure out all the factors of 84, see that that's 2 squared, and then I can write it out as log base 2 of 3 plus log base 2 of 2 squared plus log base 2 of 7. Well, this one simplifies. What does log base 2 of 2 squared simplify to? Log base 2, 2 to what equals 2 squared? Log base 2 of 2 squared is 2. So that becomes a 2. And I can't simplify these anymore because they're not a power of 2. So I can go back to this is equal to 2 plus log base 2 of 3 times 7, or 21. That's the exact answer, as simple as we can get with least number of logarithms written out. So when they want the exact answer, I'll call this is the exact answer. This is what they're looking for. So key to a problem like this, can you find a power of 2 hidden in these two things multiplied together? There's a 4 hiding in there. That gives me a slightly simpler form of log base 2 of 2 squared. Otherwise, 3 and 7 don't come out to be a nice anything simpler. So the exact answer, 2 plus log base 2 of 21. If they said to 4 decimal places, I simply feed 2 plus log base 2 of 21 into my calculator and get a 4 decimal answer. But if they're looking for the exact answer, I recognize, oh, there's a power of 2 hiding in there. That gives me some simpler, slightly simpler answer. Let's do the same thing here. This time, though, instead of combining them and multiplying 9 times 12, what do we see here? Log base 3 of 9. Do you recognize that 9 is 3 squared? And log base 3 of 3 squared is equal to 3 to what power equals 3 squared? Oh, 3 to 2 power. So log base 3 of 3 squared is 2. Log base 3 of 12, well, that's 12 is 3 times 4. Oh, so that becomes log base 3 of 3 plus log base 3 of 4. Oh, look at it. Log base 3 of 3 is, what do you think? Log base 3. 3 is 3 to the first power. Log base 3 of 3 is 1. So now, look at what I got. I know log base 3 of 3 squared is 2. Log base 3 of 3 is 1. And I have leftover log base 3 of 4. So the exact answer, as simple as possible, is 3 plus log base 3 of 4. That would be our exact answer. Otherwise, feed it to your calculator and get 4 decimals or however many they want. So see how whenever I have a base b, I look for multiples of b inside of there that will let me slightly simplify that logarithm. Find powers of your base, and you can right away find an exact number for that. So another rule, I guess we could put up another rule up here in our notes, in our rules of logarithm, that log base b of b to any power, we'll call it b to any power, how about p? B to the power of p. Log base b of b to any power p is equal to p. B to the p equals what's in there? Yeah, that makes sense. So this wouldn't be a bad rule to write down in your notes. Log base b, and if I can find some power of b in the parentheses, I can turn that into, oh, I know that's whatever power that is. So if I come back down to here, I see that this is equal to 3 squared. 3 is equal to 3 to the first power, and that's why that becomes 1. So recognizing pieces allows us to simplify some problem. So let's now look at this next one. Can we simplify this? Well, let's see. Let's do what we did before. Can we recognize any powers of 3 in 35? Well, I know 35 is, what is that? That's 7 times 5. Well, I can't get anything extra out of that. And 7 is prime, so there is no power of 3. Oh, so what can I do here? Well, I can remember my division rule for logarithms. When I'm subtracting logarithms, remember, I'll just write it down here, log of a divided by b is equal to, I'll give myself a little more room here. Remember that when I'm dividing numbers, that's the same as log a minus log b. Oh, look, I have log something minus something. Oh, rather than try to find a power of 3 in there, I know that this is the same as log base 3 of 35 divided by 7. Ooh, and I see that that is simplified down to log base 3 of 5. And I can't get any simpler. 5 is not some power of 3, so there is my exact answer. Simplified. It's kind of like reducing fractions, but using logarithms. We're simplifying this to something small, something simpler. Recognize the division rule makes this a simpler logarithm, just like reducing a fraction. I'll get the same number if I have a non-reduced fraction, but this is simplified to an exact answer. If I wanted the calculator, I could have fed this original thing into my calculator, but it's just more steps in my calculator. This reduces the number of steps in my calculator. But if they want it to decimal, I stop there and feed that to my calculator. You good with that? Take a little mind break. Think about what you're going to do after finals. Anybody traveling? Going very far?
I'm going to Texas, to Austin.
Ah. I lived in Austin during my, just after I got married. Went to grad school there for electrical engineering. Enjoyed Austin. Never got to Galveston, though. Went to Houston. And what's the town halfway between Houston and Austin? Where they make Bluebell ice cream. There's a place there. Did go to Padre Island. Fun place to go. Fun times in Texas. And nice and warm there. They had a drought a couple years ago, but doing better there. Anyone going skiing? I have some friends, they love to go out to Denver during Christmas. I'm jealous of them. My son has his in-laws love to ski, and they'll go for, you go to sundown. How long does it take to go down the hill at sundown? 30 seconds? Oh, maybe a couple minutes if you go slow. Out there, An hour later, you're going to find it at the bottom of the hill. It's like, wow, that's a fun time skiing. Maybe one day. I'm not that great a skier, but I think I'd enjoy it. And my kids, maybe grandkids. Got a couple grandkids coming. Maybe when they're old enough, we might do that. And I'll be ready. Probably retired by then, have this spare time. My plans over Christmas, get ready for my classes in the spring semester. All right, good. Good little mind break there. All right, now let's come back to some working on a little bit of math. Now these, there's nothing you can do if you have an x and a y. All you can do is put it in maybe a simpler form. It's like, well, wait a minute, that's a pretty simple form there. They'll be asking you to put it in a alternate form, like no exponents. Okay, so although those are perfectly fine forms, and that you can, and it tells you the rule, they'll say, well, put this in the form that's simpler, or that's no exponents are involved. So what rule do I apply here? Well, remember one rule. I don't know if I had it written down at the top. Log, well, I guess we sort of have it here. B to the y equals x. Oh, here, I have this one. Log base b of b to some power is that. Let's do another one just to make it clear. When I have the same number to a power in there, it's simpler. But again, there's another rule. Log base b of some number, any number, not necessarily b, to some power p is equal to p times log base b of that number a. So if a is some different number, I can't simplify it more if I don't know what a is, but I can bring out the power out in front of the logarithm. So I turn an exponent into a multiply. So log base b of a to the p is same as p times log base b of that number a. So we'll use that down here. And we also need to use our division rule. So let's do the division rule first, and then we'll do the exponent rule, because you want to be very careful not to get them messed up. Let's do the division rule first, then the exponent rule. So division rule, so I'll put div. Div rule is these two things divided means that's the same as log base 5 of x to the 5th minus log base 5 of y to the 3rd. Do the division rule first, and now the exponent rule. Whatever this exponent is, it comes out in front of the log base 5. Now we can take away the exponent. That becomes 5 log base 5 of x minus 3 log base 5 of y. Taking away the exponents, there is my alternate form. And we can't solve for x or y. We just have a slightly different form of the same number that maybe, as I have other equalities, will help me simplify this. But for now, that's taking away exponents, turning into a multiply by a logarithm and a subtract. So using our rules, we're just simply going to a form without exponents. Now you may be given a problem that says, put this in the form of x and y with exponents instead of a subtraction. Well, then you're just going the other direction. You may be, I don't think you're given a problem, but I haven't checked all of them. Remember, you can go either direction. If you're given this, and they say put it in a one logarithm with a exponential form, well, that means put this back in the equivalent form like this. Let's do another practice. Again, do the division first. The divide rule is log base 4 of x squared minus log base 4 of z cubed. The division rule. Any two numbers divided, logarithm of becomes a subtracting the bottom one from the top one. Now apply the exponent rule. Bring the exponent out in front. That becomes 2 log base 4 of x. 3 comes out into the front. Minus, the minus stays there, doesn't change. Minus 3 log base 4 of z. Just practicing manipulating logarithms. And then one more. Same kind of thing. And don't let this fool you. Just because you see a 3 here, even it's not 3 to some power. It's a to the third power. There's nothing I can do except bring that 3 out into the front after first applying the division rule. So let's do the division rule first. Log base 3 of a cubed minus log base 3 of b squared. And the rule of bringing the exponent out to the front, that becomes 3 log base 3 of a minus 2 log base 3 of b. That 3 and that 3, because it's log base 3, we can't do anything special. We just bring that out to the front of the logarithm. Exponents turn into multiplies. Now a real mind break, or call it a changing gears now, we're leaving logarithms behind and going back a little further into the past and looking for the inverse function. And let's write down a few rules. How do we do the inverse? We have some space down here to write our inverse rules. If we're looking for inverse of f, how do we do it? Well, we have some function, f of x equals something. Something that's, say, x squared plus x plus 2 or something. Remember what we do. We say y equals that. And then swap the x and the y's. So write it out. Y is that. Now we swap x and y's. X equals y squared plus y plus 2. And then solve for y. So let's do that with this one. First of all, we'll do y equals 1 over x minus 8. Now we swap x and y. We have x equals 1 over y minus 8. We want to get y by itself and not underneath. So let's multiply, or just do the inverse of both sides. That's probably easier. Do the inverse of both sides. That means we'll take 1 over everything. So 1 over x equals, well, 1 over y minus 8 is the same as y minus 8. And now I can add 8 to both sides, and I have solved for y. 1 over x plus 8 equals y. See how adding 8 to both sides? So therefore, the inverse of f of x, f inverse of x, equals 1 over x plus 8. Y equals f of x. Swap x and y. Solve for y in whatever way you can. And now you have the solution. let's do that again for this one. Y equals 1 over x plus 5. Just like we did before, if I want to get, well, I have to swap x and y. Now I get x equals 1 over y plus 5. Do the same thing. Inverse both sides. Just because I see I want to get y by itself and not underneath, I know taking 1 over both sides will still be equal. So 1 over x equals y plus 5. 5. Now, subtract 5 from both sides. And I get 5 to cancel out. And I get 1 over x minus 5 equals y. Equals f negative 1 of x, or f inverse. It's a proper term for it. So f inverse equals 1 over x minus 5. Just a little memory review. And one more, just again, for more practice, recognizing the forms more quickly as we practice for the third time. Y equals 1 over x plus 3. Swap x and y. And because I have a fraction and I want to get the y on top, do the inverse of both sides again. And now subtract 3, and I'll have y by itself on this side. 1 over x minus 3 equals y. Therefore, f inverse of x equals 1 over x minus 3. Now, you're not always going to have fractions to worry about. Remember the step. You set y equals to that function, swap x and y, then solve for y. Get y by itself on one side of the equality, and you have then found f inverse of x. And I'll leave that last one blank for you to work through. If you can work that fourth column out on your own, you're doing pretty well and should be ready for those problems on the final. And since I'm going to have some polynomials, I've already written this out, but I forgot I gave you space to write out this. Remember, when I have a problem, ax squared plus bx plus c, when I have that equal to 0, I know the solutions for x are x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And while we're here, remember, negative b over 2a is the vertex. It's going to look like a parabola of some sorts. The vertex is that center point, negative b over 2a. Is going to be that x value somewhere in the graph. I know that that's my vertex. Where it crosses, that's my solutions, where x and that parabola crosses the x-axis. But we're given problems that have nothing to do with the quadratic equation. We're being asked to show me what f composition g is, the composition of functions. And over here I'm going to write in my notes, because I like it written out this way better. F composite g of x, I like to write f with g of x as its input. That's what that means. I like this format better because I think to myself, oh, whatever g is, I put into where the x is in f. So let's do that for this one. F of g of x, I'm going to quickly write out that is the same as f with g as its input. Well, I'm going to write it out this way. F of x equals 3 times its input minus 3. So f of x, f of g of x is equal to 3 times its input minus 3. And its input is g of x, negative 9x plus 1. That's the way I think of when I think of composite functions. F takes something, its input, and subtracts 3 from it. Let's take g and put it there when I'm finding the composite f of g of x. And now it's just a matter of multiplying things out. That's a negative 27x. 3 times negative 9 makes 27 times x, negative 27x, plus 3 times 1 minus 3. And those cancel out, so I get negative 27x. So the composition is actually a simpler function, which makes our mathematicians and our calculators happy. Sometimes the composition is more complicated, but in this case, the composition is a nicer, simpler calculation. So F composition G. Write that out. I think you'll find it easier if you think about it this way. The F dot G, it's so easy to make it. What do they mean, F dot G? Well, put G as input into F. Uh-oh. F of F, what do they mean by that? Well, that just means I take F, its input is F of X. All right, well, what is F? Well, that's 3x minus 3, all right? So F is 3 times some input minus 3. Well, what's the input? Well, it's F of X, 3x minus 3. There's F, and F, taking that as its input, that's a perfectly fine mathematical function, and now it's just a matter of multiplying out. 9x minus 9, and then minus 3, becomes 9x minus 12. And one more. Now they're going to give you a problem which is going to have also g of g. Did I give you that? I only gave you g of f. We'll do g of g for an extra one. I'll add that as an extra. Can we do g of g? But let's do g of f now. Well, same. Going to take the same approach. Remember, that's the same as g with f of x as its input. All right, and g is negative 9 times its input plus 1. So I'm going to write it this way. Negative 9 times its input minus 1. Double check. Oh, plus 1. Negative 9 times its input plus 1. And f of x is 3x minus 3. Double check what f of x is. Yeah, 3x minus 3. Put that in to the input of g. 3x minus 3. I find this is very helpful for me to get this composition just right. Think of the input for G is some number that I put in parentheses. Oh, that number is what f of x is. Now, multiply it out. Negative 9 times 3, negative 27. Uh-oh, watch the signs. Negative times a negative 3, or sorry, negative 27x. Negative 9 times negative 3 is a plus 27. And plus a 1. Now that becomes negative 27x plus 28. G composition f of x. Take G, feed x into its input. Couple practice of those. I think there's only one problem where you have to do the composition, but you're going to be given two functions. You're going to have to do the composition of all those f of g, f of f, g of f, and g of g. This one, we're just looking for, well, they're going to also ask you for what is f, oh, actually here. They're going to ask you for f of certain inputs. So we'll do that. Let's find our vertex. That goes back to our quadratic formula. Remember, the vertex is negative b over 2a. Well, this is b, this is a, and this is c. So it's going to be equal to negative 12 over 2 times a, 2 times negative 4, or negative 12 over negative 8. Reduce that, divide both sides by 4, and I get 3 halves. That is my vertex. If I just want to write out in general, okay, that's going to be some parabola. Since I'm multiplying by a negative value, it's going to be going down. It's going to, let's see, when x is 0, oh, I'm going to get 8 out of it, so I know it's going to cross here at about 8. Well, not about 8, exactly 8. And the vertex is at 3 halves, 1.5. Well, now it's just a matter of finding its value when x is 1, or 2, or negative 1. So, negative 4x squared plus 12x plus 8. All you do is put the 1 where the x is. Negative 4 times 1 squared, or times 1, plus 12 times 1, plus 8. Or, negative 4 plus 12 plus 8 is 20, or 16. So at 1, it's going to be up here around 16. If I had a 1 there. So the graph is going to be 16 there. And at f equals 2, let's see, it should be coming back down. Let's see what we get. F of 2 is negative 4 times 2 squared, or times 4, plus 12 plus 8. Oh, sorry, plus 12 times 4. Ooh, 12 times 4 is 48. Oh, sorry, 2. Sorry. Let's fix that. Forgot what my value of x was. Plus 12 times 2 plus 8. Well, that's 24 plus 8. That's 32. Negative 16 plus 32. Negative 16 plus 32 is 16. Oh, look at that. F of 2 comes back down to about 16. And f of negative 1, well, we just feed a negative 1 in there. That's negative 4 times 1, negative 1 squared times 1, plus 12 times negative 1, or minus 12, plus 8. It's just arithmetic now. It's negative 4 minus 12, that becomes negative 16, plus 8, that becomes negative 8. So I'm over here at negative 1, I'm down here at negative 8. But all we did there was put that value of x, or put that value into where x is. Now there will be one problem having to do with the exponential problem, the most practical problem ever, but probably the most scary problem, the word problem having to do with investments. The one that you'll be using when you go to buy a car, a house, pay for a car, pay for a house. Maybe somebody pays you, you invest your 401k. Let's get this formula down. This is something you could have in your notes. The future value of your investment, and it doesn't matter what letter you use. Let's see, we'll call it I'll call it V, the future value. Some people put FV, but I'll put V. The future value of your investment is equal to your investment, your initial investment, I'll call that principal, P, times 1 plus the rate of interest divided by the number of times it's compounded yearly to the power of the number of times it's compounded yearly times, they like to use T, but I'm going to put Y in here because I think Y is a better variable. Because Y represents years of investments R is the rate of interest. N is the number of compounding per year. And P is my principal, my starting value. Principal. Or my initial investment. You don't have to worry about how they figured that out. Just write down that formula as a example. The most likely exponential problem that you'll encounter in your life is this problem. And fortunately, the banks and the computers will do this for you, but they want you to know this in algebra. Well, now we're given the problem. All we have to do is figure out what goes for what letters. Well, there's our investment. That is our P, $1,000. So P is 1,000. It's our initial investment. 30 years, that's the Y. Y equals 30. Interest rate of 5%. Now you got to be careful here. The R has to be mathematically 5%. So remember, in a calculator, R is going to be 0.05. 5%, N% means N over 100 mathematically, or 5% is 0.05. That's often the trickiest one. The next trickier one is, what is N? Compounded per year. They don't tell you. They give you a clue right here. When you see monthly, that means it's compounded once every month. N equals 12. Other times, depending on the problem, they'll say semi-annually. That means N equals 2. Or yearly means N equals 1. Daily, N equals 365.25. But as long as you know that formula, and now you just have to put it into the equation, or put it into the formula now, all I do is put in my calculator 1,000 times 1 plus r, 0.05, over n is 12, because it's compounded monthly. Take it to the power of n times y, or 12 times 30. Well, if I want to simplify my life, 12 times 30 is 300 plus 1 times 10 times 30 plus 2 times 30, or 360. Plug it into my calculator, and I get my answer. And since we're out of time, I'll let you put that in your calculator. But you'll have your calculator to do this. This is the hardest part, recognizing what all the p's, the r's, the n's, and the y's are. They'll not make it super tricky, but the most of the mistakes I see people have made is they forget 5%. Remember, a 5%, you have to put that mathematically 0.05. Those other practices are there for you. You can keep to study for the final. And the final, remember, is, according to the official time, and I just sent an email out to remind you, Tuesday, 9:40 to 11:25. And there's only one chance. They're not giving us 2 chances. So be ready. If you can do those review problems, the review exam, you'll get points for that, extra credit. Do that, and you'll be prepared. Have a wonderful day.